what we discussed last class? What did we talk about? We talked about matrices. What are matrices? Okay, just rectangular arrangement of numbers. And if it's a matrix of all real numbers with n rows and m columns, what set is that from? The set of all real matrices. Let me say this is from Cosine, yeah. Okay. And then what else? Okay, alright, before that we looked at vector and for vectors. Okay. And then we looked at we looked at block matrices. And then some special matrices, m cross m, in, and then we also looked at and then upper triangular and lower triangular matrices. Okay. Then yeah, so we looked at two equations. Then an addition. And what did these two lead us to? What idea about the set of n cross m matrices? Right, the set of n cross m matrices, they form a vector space. Okay, because they are closed under scalar multiplication and matrix addition. And then okay, we looked at the transpose operation. Transpose operation simply converts n cross m to m cross m. It switches the rows and the columns. Okay. Then and finally we started discussing about this multiplication. When can you multiply two matrices A and B? What is the condition on these two? Yeah, number of columns in A should match the number of rows in B. So that means if this is n cross P, this has to be P cross something. It can be any number, M. And if that is the case, I'll get a matrix C. What will be the size of C? N cross M. It will inherit the number of rows of what? Number of rows of A and number of columns of B. Okay. And what is, how do you express each element of the matrix C? What is the ijth element of this matrix C in terms of elements of A and B? Summation over what? Okay, some variable, some dummy index. Kj or Jk? Okay. And what is the summation over? That means you take the elements of the ith row of A, jth column of B, and then you multiply the individual elements, and then you add them all together. Okay. And then we looked at simpler cases of matrix multiplication, right? A multiplied by vector x. Let's say this is n cross n. This is n or m. Where should this be from? Rn? Rn? M. Okay. And what will I get? If I do this operation, what would be the size of this? It will simply be Rn or m cross 1. Okay. But not just that, right? We looked at what was really going on here. No? When you post multiply a matrix by a vector, what is really going on? What is this y? Yeah. Yeah. What is this y? Oh, you're right. Go ahead. What is it? Inverse. What can you? So you, if you post multiply a matrix by a column vector, you get a column vector. What can you say? Right. Y is a linear combination of the columns of A and sorry, yeah, columns of A. And what is the role of X here? Right. So Y will simply be equal to what? Okay. Can you tell me the exact expression in terms of columns of A and the elements of X? A, N or M? Okay. So post multiplying A by a column vector simply means you're taking the linear combination of the columns of A. So if you want to take the linear combination of columns of A, all you have to do is multiply the post multiply the matrix by some vector X. Then, right? So if you have a matrix A, and if you want to take the linear combination of the rows of A, then you multiply it by X transpose. Let's say this is N cross M or N or M? N. Okay. And what do you get? No, no. Oh, what do you get? If you pre-multiply a matrix by a row vector, do you get a column vector or a row vector? You get a row vector, and we've chosen the convention of writing row vectors with a transpose. And where is this from? R, M. And what is this? In terms of the rows of A. A, X, N, A, N. Okay. So if you pre-multiply by a row, all you're doing is you're taking the linear combination of the rows of A, and that is essentially your. Okay. All right. This is where we stopped. Are there any questions about this? Okay. All right. Now, okay. With this, we are now ready to look at the general case here and try and understand what's going on. But before that, we'll take a look at two more matrix multiplication operations. The standard inner product. Okay. So, what is the standard inner product of two vectors x and y from Rn? What was it? It was expressed like this. Now, in the matrix multiplication sense, does this make sense? I mean, does this fit into this picture? If you think of each of this as a matrix, a column vector, right? Or a matrix that's from R n cross 1. Okay, are you allowed to do this? Yeah, we are. No, this is from R n cross 1. This is from R, because you've taken the transpose. This is 1 cross n. These two match, and what you get when you do this inner product, you get a scalar. A scalar is nothing but plus 1, so that's fine. Right? I'll call it some z. Okay, and you'll find that this exactly matches this definition as well. Now, that's the standard inner product. Now, the fact that we called it an inner product probably already tells you that there must be an outer product, right? And there is. And it turns out outer products are as important as inner products. Okay? The idea is very simple. If you're talking about inner products, at least the standard inner product, you're talking about multiplying a row by a column. row by a column. Can I switch the two? Okay, yeah. Can I do multiplication like this? Assuming that both x and y are from Rn. Is that a valid operation? That means, can I do this? What is the size of this? Or where is this from? These two match, and all that is all that matters. And what is the resultant? Where is that from? N cross? Right. What you get is n cross n matrix. Okay. Now let's just do an example to see what that matrix will be like. Let's say I take x to be 1, 2. What will be x, the outer product of x with respect to y? So that will be x is 1, 2 multiplied by minus 1, 1. And if you're not clear what to do there, apply this, just this expression. And notice that p is 1 in this case. That's all. That means you'll only have one term in the multiplication, in the summation. Yeah, okay. So we were multiplying 1, 2 with minus 1, 1. What will you get as the resultant? It will be a 2 cross 2 matrix. What is the first term? How is this matrix? Okay, let me ask you this way. How are the columns of this matrix related to x? See, the columns of this matrix are scaled versions of x, right? So this is minus 1 times this. This is 1 times this. Okay. What about the rows of this matrix? They are simply scaled versions of the y transpose, right? Minus 1, 1, minus 2, 2. And the scaling exactly comes from the other vector, right? For the columns, the scales come from y transpose. For the rows, the scales come from x. Okay, all right. Now that that's clear, let me just ask you this. Is it possible for me to, if I do an inner product operation, is it possible for me to get a rectangular matrix? No? NM. So the example that we saw here resulted in a square matrix. Can you get a rectangular matrix if you do the outer product between two vectors? Right. So what if I choose my 1, 2, but I choose, so this is from R2, but I choose this to be, what would I get now if I multiply these two? This is from R3. This is your x, this is your y transpose. How many columns will you get now? What will be the size of this? Where will this matrix be from? R? 2 cross 3. What will be the columns of this matrix now? I mean, we know that the columns will be scaled versions of this, and the scales come from here. It's easy. 1, 2, minus 1, minus 2, 3, 6. Let's go 2 rows, and the first row is simply this because the first scale is 1. The second row is 2 times this. Now with that, we now move on to talk about the general case of multiplying two matrices. It's A times B. We'll assume again n cross P, P cross n. What you get will be n cross n. Okay, and if you just use this formula, you can do the matrix multiplication. Okay, there are four ways in which you can interpret what is going on there. Okay, I'll just list them first, and then we'll go through them one by one. First one is called the inner product inner product interpretation. The second one is called the column interpretation, row. The fourth one is the outer product interpretation. And all of them are useful in their own right. Okay? In different applications, you might want to look at matrix multiplication like this. Some other application, you might want to look at it like this, and so on and so forth. Let's start with this now. Okay? The inner product interpretation simply tells you that if you want to multiply two matrices, okay, like this, the ijth element of the resulting matrix is simply the inner product of the ith row of A and the jth column of B. Okay. Now let's check if that's in fact correct here. Right? Now here, Cij is this sum, right? You have Aik. Where are these elements from? From the A matrix. I is the row index, and you're going over all k. That means these elements come from the ith row. Okay. This is bkj. K is the column index. J is fixed. That means these all come from the jth column of P, and you're multiplying the individual elements and adding them together. If you look at the matrix A, right, the ith row is simply A1, AI1, AI2, AI, right? And for the B matrix, what is the jth column? B1j, B, right? We're only interested in the ijth element of C, so the other columns and rows don't matter. Okay. Now, this is a row, this is a column. So we use the convention of writing this as A tilde I transpose. Okay, and we use the convention of writing this as B j. Cij is nothing but, what is it? A the ijth element is simply you take the ith row, jth column, and take the inner product. That gives you the ijth element. That's one way of, that's the inner product interpretation of what's going on with matrix multiplication. Yeah. We'll again do, maybe what we will do, we'll reserve this for an example. Okay. Okay, if you multiply these two, what do you get for C? What will be the size of C? 2 cross 3, what will be the elements? Can you tell me the elements? In fact, I'll write it down here. What is it? 3. Twelve is it? Yeah. Okay. How do you obtain this element 1 1 C1 1? You take the first row, first column. If you take the inner product, you get 3. I mean, that's how you compute it, right? Similarly for all of them. So what you have is okay. All right. Now the next idea, the column view or column interpretation of. How many columns does C have? It has the same number of columns as B. Okay. So it turns out in the column view, you can talk about the individual columns of C. Okay, that's the ith column of C. Is simply A, okay, multiplied by the ith column of C is simply the first matrix A post multiplied by the ith column of B. Okay, what does it mean? So what does it say about the ith column of C? How is it related to the columns of A? Okay, how is the ith column of this matrix C related to the columns of A? I mean, go back to thinking about post multiplying a matrix by a column vector. Yeah, the ith column of C is simply the linear combination of the columns of A, and the exact mixture of that linear combination comes from the elements of the ith column of B. Okay, maybe that's a lot to think about, but it's not that complicated. Okay, it means this is simply so if you express A as a block matrix in terms of column vectors, you have A1, A2, A, M, no, AM, no, AP, because this is N cross P. Yeah. If I were to write down the ith column of B, what would be the individual elements here? It would be B, it's the ith column, it will be 1, I, is that correct? B, 2, I, and how many do I have? P, I. Here, because this is from P cross N, there are P rows in B. So what will this be? Matrix post multiplied by a column vector. So this will simply be B1I multiplied by A1 plus B2I multiplied by A2 BPI multiplied by, okay. See, the nice thing here is see, maybe that original expression we had where Cij is the sum of Aik and Bkj, that's too complicated. But the column view at least gives you some nice way of looking at what is there in C. You can look at the columns of C completely independently of each other. Okay. The ith column of C, or every column of C, is entirely determined by the columns of A. Okay. And the specific ith column is determined by the columns of A and the elements of the ith column of B. Okay. And the exact operation that is happening is you're taking the linear combinations of the columns of A, and the exact mixture for the ith column of C comes from the ith column of B. Is that clear? Okay. Now, let's see. Don't do the inner product operation. Compute the columns of C using this expression. That means take the linear combination of columns of A. For computing the first column of C, take the linear combination of these using the first column of B. Same for second and third, and let's verify that we get the same answer. Is it clear? Okay, let's see, we are talking about the first column of C, right? C1 should be a linear combination of the columns of A, and the exact mixture for the linear combination comes from the first column of B. Okay, that means this is simply A multiplied by B1. This is 1, 3, 2, 4. This is 1, 1. Let's not do the inner product. This is nothing but 1 times 1, 3 plus 2, 4. And what do I get? I get 3, get 7. That's exactly what we get here. Okay. You can again quickly verify that these are also okay. Yeah, it should be the same. Okay. So if you are talking about a huge, so let's say you're multiplying two huge matrices, okay, and you're only interested, let's say for some reason you're suddenly interested in the 100th column of C. You don't have to do the entire matrix multiplication to find out the 100th column of C. All you have to do is take the columns of A and then do what? Okay, okay, let's say this has got a million rows and a trillion, a million rows and a trillion columns and a billion rows. But you're interested in the 100th column of C. Would you have to do the full matrix multiplication to get the 100th column of C? What would you do? You still need A. Okay, right? You take the 100th column of B and you simply do this to get the 100th column. Is that clear? Okay. Okay. I mean, you're probably already guessing what this is. What do you think I'm going to say here? So there we talked about the columns of C. I'm talking about the row interpretation. So I'm going to say something about the rows of C. Okay. What do you think I'm going to say? What can I say about the ith row of C? You remember when we talked about row vectors, we were pre-multiplying. That means, no A transpose. Here, B, A, what? I. A cannot be AI, no? AI, it cannot be the ith column. Yeah. So the ith row of C is nothing but the linear combination of the rows of B. Okay, and the exact mixture for the linear combination comes from the ith row of A. Okay, let's write this down again. So we can write B as, if you write this in the block matrix form in terms of row vectors, so this will be B1 transpose, B2 transpose, B, how many rows do we have? Okay, what about this? What about the ith row? What will this be? 1i or I1? I1? Yeah, I. Because it's the ith row, the first index is I. AI1, AI2, AI. That means this will simply be, what will this be? AI1 multiplied by B1 plus AI2 B, and then AI3 B. Let's verify that. Here. Tell me what is this second row of C? So for computing the second row of C, we only have to consider second row of A. So that will be 3, 4, and we of course have to consider all of B. You can compute it like this, not using the end product. So what will this be? This will be 3 times 120 plus 4 times 1 minus 1, 3. And that will give me 3 plus 4, 7. 6 minus 4, 2. Okay, that's the second row of C. Okay. See again what these two interpretations tell you is, let's say you have a matrix A, okay, and the columns of A mean something to you, and you're interested in doing some operations on the columns. When I say operation, we're talking about doing some linear combination. Okay, then all you'd have to do is post multiply this by a matrix B. Okay, and the elements in B, or the elements in the columns of B, will tell you the exact linear combination that you want to take of the columns of A. Okay, if you have A and the rows of A tell you something interesting, or you're interested in manipulating the rows, manipulating in the sense you want to take the linear combinations, then you simply pre-multiply by the matrix B, where the row elements in the rows of B will tell you how, will determine how you want to manipulate the rows of A. Is that clear? Okay. All right. Now we come to a very interesting way of looking at matrix multiplication. Okay. Okay. Now we know that we can write A and B in a block matrix form, right? And we are interested in C equals A, B. Okay. Let's say we choose to write A and B in block matrix form, but we choose to write A in terms of columns of A and B in terms of rows of B. Okay. So what will that be? Then A is simply A1, A2, A, what? How many rows how many columns does A have? T, that's what you assume. Yeah. What about B now? Well, the rows of B, the convention we've chosen is to write it like this. Right? Now we want to multiply these two together. That means A1 to AP remember when we discussed about block matrices last time, I said one reason for writing things out in a block matrix form is you can manipulate block matrices like you would manipulate the matrix if it was written down fully in terms of its individual elements, the scalars, right? Let's see that is possible. Okay, let's not worry about why that is possible. Let's assume that it's possible. Okay. Then this, you can think of this as a row block vector. Yes, this is like a row vector, except the individual elements are not scalars. The individual elements themselves are something. Okay. What is this? So this is like a row vector. This is like a column vector. And what is this operation when you have a row vector multiplied by a column vector? That's a standard inner product, right? X transpose Y. And what do you do when you take the inner product like this? You take the first element here, multiply them together, take the product of these two, so on and so on. Of course, the sizes have to match, right? Only then you can take the inner product. And then you add the products together. Well, let's see if we can do the same thing here. I'll do this. Okay. Now the question is, if you treat this as a row vector and this as a column vector, can you simply interpret this as an inner product operation? Okay, that means I take the product of these two, A1 multiplied by P1 tilde transpose, and then I take the product of the next two, and then I add them all together, AP, PP, right? Am I allowed to do, okay, I mean I've written it down like this, but am I allowed to do something like this? Is this, I mean, what I mean by that, am I allowed to do this individual multiplication here? Is that a valid operation? I am doing a matrix multiplication here, but is that a valid matrix multiplication? I mean, all you have to do is check if the intermediate, if the rows of this match with the columns of this, that's all. No? Do they match? Where is this from? Where is A1 from, and where is the first column of A, or where are the columns of A from? Where are the rows of B from? Remember, A is R n cross P, B is R P cross M. They match? The columns are from Rn cross 1. Where are these from? Well, as long as these two match, it doesn't matter what these two are. M. Right? So this is allowed. And what do I get if I multiply these two together? So what I do get is this. If I multiply this whole thing together, I get Rn cross M. And that is the exact same size as C. What is the size of C? N cross M. This was N cross P. This was P cross M. What is the size of this? Same, N cross M, N cross M. So this looks like this is a completely legitimate operation. Okay. So this simply means in the outer product view, and how many outer products do you have? P outer products, right? In the outer product view, you're saying we can think of this resulting matrix C, which is the product of two matrices A and B, as the sum of P outer product matrices. And what are those P outer product matrices? Those are simply the outer products of the columns of A with the rows of B. Okay, here the outer product. Right. Outer product is always with the column and the row. Inner product is a row and the column. Right. C is simply the sum of P outer products, and the P outer products come from you taking the outer product between the columns of A and the rows of B, because there are P columns and P rows. Sorry, P columns of A and P rows of B. Is that clear? Okay. Maybe this is too confusing. Let's just verify that we do get that matrix if we take this approach, right? How many? Okay, in this case, how many outer product matrices will we get with this in this particular example? 2, right? Because P is 2. Okay. What is the first one? So the first outer product matrix will be A1 with, what do you get here? You can tell me that one first. So that's this with this. What do you get? Huh? 1, 2, 0 is it? Okay. Yeah. Is that okay? Well, when you take the outer product, the columns of the outer product will be scaled versions of A. The rows of the outer product will be scaled version of the second, the row vector. See, this is 1, 3. So 1, 3, 2, 6, 0, 0. They are all scaled versions of A. The row is 1, 2, 0. The two rows are scaled versions of each other. Okay. What about A2? Okay. 2. If you add these two, what do you get? So the sum of these two is supposed to be your C. 3, 0, 6, 7, 2, 12. Okay, so that's another way to look at matrix multiplication. Okay. See, the place where this becomes useful is, it turns out outer products play an important role in projection operations. Okay, where you take a vector and then you find its shadow on a subspace. Okay, so one way to think about this is, you can think of this matrix multiplication as if you are decomposing your space into different projection operations. Okay, the details of this will become clear later on when we talk about orthogonality and in the orthogonality module. So don't worry too much about it. Okay, so those are the 4 views, and again you have to be very comfortable with all 4 of them. Okay. Now I'll just point you to one interesting symmetry in this whole thing. In the outer product view, right, you take an inner product, right, between a row vector and the column, row vector and the column vector, but the individual elements themselves are not scalars but column vectors and row vectors. In the inner product view, it turns out you can come up with a similar view for the inner product, instead of viewing A as block matrix of columns and B as a block matrix of rows, we can ask what happens if you look at it the other way around. Okay, let's say we look at A as a block matrix of rows. Okay, and B as a block matrix of columns. So AB would become B1, B2, B. How many columns does it have? B. Okay. Here you're multiplying a row with a column. That was an inner product. You're multiplying a column with the row. What is this operation? It is an outer product. Okay. And what will the individual elements of this be? If you do an outer product, so if you do an outer product between AB and CD, what do you get? What are the elements you get here? The first element is AC, second element is AD, BC. So what will be the matrix that you get now? Okay. So on and so forth. What about the ijth element? What will be the size of this matrix? N cross M. What will be the ijth element? Just think about this. What was the ijth element here? What is the first? I mean, what was this? Let's say this was some K matrix. What was K1, 2? It was the product of the first element here and the second element there. Ith row, jth column. So what will be the ijth element here? Ith row, jth column. What is this? What is the expression for the here exactly? Okay. So in the inner product view, it's an outer product of inner products. Here it's an inner product of outer products. Okay, or something like that. Okay. So you see a nice symmetry that comes about. Okay, all right. That's all I wanted to say about matrix multiplication. We now quickly talk about I'll remove this. We'll now talk about linear transformation. And before we proceed to linear transformation, let's just talk about some properties of. I won't talk about all of them. These are there on the lecture slide, so you can look at them. We'll just talk about a couple of important ones. Matrix multiplication is not commutative. Okay, you might be able to find special matrices where this is satisfied, but in general this is not true. You cannot flip. Okay, in fact, the multiplication operation might not even be defined. Okay, if I have A is n cross p and b is p cross n m, if you flip these two don't match, so you cannot even do that. So this is an important one. And another useful property is this. It turns out this is fairly simple. In fact, this also extends to if you have A1, A2, AL, a finite number of matrices, and you take the transpose, you can simply express this as the product of the individual transposes, but in the reverse order. So this will be AL transpose A L minus 1 transpose, and these are easy to show. A1 transpose. Yeah. So these are the only two major ones. The rest you can take a look at the slides. In fact, a good idea or a good way to get a handle on matrix multiplication is to try and prove things like this, that AB transpose is in fact B transpose A transpose using these different views. Okay. You remember the end of last module we talked about linear functions, right? And we looked at functions f that mapped from Rn to R, and it had to satisfy the superposition principle for it to be a linear function. And we said that any linear function of x can always be written down as x, where W transpose is a vector from is a fixed vector from Rn. Sorry, W is a fixed vector from Rn, right? As a standard in the product between some fixed vector and this vector that goes into this as a function, as an argument into this function. Now this is maybe restricted, right? You could ask, why should we only? I mean, what about functions that map from not from Rn to R, but again some higher dimensional space, right? Those are called linear transformations or linear maps. So if you have a function f that maps from Rn to Rm, okay, that means if I take a vector x from Rn and I send it as an input to this function, what I get will be another vector. I don't get a scalar anymore. And where will y be from? Be from Rm. Whereas what went in, okay. Now this function is a linear transformation or a linear map if it satisfies the superposition property. And what does that mean? Means if I have a vector x that gives me f of x1, if I have a vector x2 that produces f of x2, then if I compute f of alpha 1 times x1 plus alpha 2 times x2, where the two alphas are some scalar. If I know this and I know the scalars alpha 1 and alpha 2, then I know what the outcome of this is. This is simply alpha 1 times f of x1 plus alpha 2 times f of x2. And if this is satisfied for all possible x1, x2 and all possible alpha and beta, sorry, alpha 1 and alpha 2, if this is satisfied, then you say this function is a linear map. Okay. The same as what we had before. Okay. It turns out there is a similar fact here, that any linear function from Rn to R can be written like this, and this is where matrices come into the picture. Any linear transformation from Rn, okay, let me just change one thing, Rn, okay, any linear transformation from Rm to Rn can be represented by a n cross m matrix. Okay, similar to what we had here. Okay, that means this function f of x can simply be written as a times this vector, and this vector is from Rm. I multiply these two. What do I get? I'm post multiplying by a column vector. What do I get here? Column vector. What will be the size? Where will this be from? Rn. Yeah. So if this is a linear function, you can always find a matrix A such that y, and if you do A times x, y will always be equal to f of x. So one of the uses of matrices is they represent all possible linear transformations. Okay, in fact, n cross m matrix represents some linear transformation from Rm to Rn. Now that will lead us to understanding why matrix multiplication is defined the way it is. Okay. let's say we have two linear maps. Okay, F that is defined from R M to R P. We have another linear map G that is defined from R P to R M. Okay, that means if I take any vector from Rm, okay, and I compute this, what will I get? I'll get some vector. I'll call it y. Okay, and where will this be from? Which space? RP, no? It maps to RP. So this is from RP, right? Now, because of this fact, that means this linear transformation, let's say it's represented by a matrix A. And what will be the size of that matrix? Will it be n cross p or p? Sorry, n cross p or p cross n? Let's look at this. F maps from m to n, then it's n cross m. Maps from m to p, that means this has to be. Okay. Similarly, there is another function that maps from p to n. Let's say that's represented by the matrix B. And what will be the size of this? Be n cross p. Okay. Now this is a vector from Rp, right? G takes inputs from Rp. That means I can say, okay, I'm going to take this and then put it through this function. And then let's say this gives me some z. And where will z be from? Rm. Okay, all right. Okay, for simplicity, let's say all of this is 2. Okay, and the function f is represented by a11, a12, a21. Okay, and the function b, g is represented by b, which is b11. Okay, now I take a vector x from, I mean everything is R2, so no problem. I take a 2 cross 1 vector, right? x1, x2. Okay. I first pass it through f. It's a linear function. Okay, I get a vector in R2, and then I pass it through G, and then finally I get Z. Okay. What will Z be? Well, if I just told you this, of course you don't know what it will be, because you don't know what exactly is happening with f and g. But if I give you the matrix, then you know exactly what is happening, right? What is f of x? I'll remove this. Let's just look at f of x first. Y equals f of x. F is represented by a. That means this is nothing but, right? So what is my y? Can you tell me what is y? You simply have to do the matrix multiplication. So this will be a11, a12, a1, a2, x1, x2. What will this be? Tell me the exact values that you get here. Yes, okay. So this will be a11 x1 plus a12 x2 and a21 x1 plus a22. Okay, that's my y. Okay, now I take this y and then I pass it through my G. And what will this be? And this gives me, let's say, some Z. But G is represented by B. That means this is nothing but B times Y. That means this is simply B11, B12, B21, B22 multiplied by Y1, Y2. Okay. Look, substitute for what this is Y1, this is Y2. Substitute it here and multiply the whole thing out, and then tell me what you get. I know it's a little messy, but yeah, if you do it carefully, it's simple enough. We'll get two elements, Z1 and Z2. Tell me what is Z1 first and then Z2. Yeah. How many? You have more terms, is it? 4 terms. Okay, all right. Okay. What about the second one? Okay. You have it? You have it? Okay. B21. To x2 is it? Okay. All right. This is a vector. Okay. Now the question is, can I express this vector as a product of a 2 cross 2 matrix and x1, x2? If I were to write it like that, what would be the first element? What would be the second element? Let me expand it. So, club the x1 terms together first. Okay, it's these two, right? If I form the first term here to be the sum of these two, and when I do the multiplication, I'll multiply those two terms with x1, I'll get these two, right? Okay, so that will be A11, B11 plus is that right? No, sorry. This will be B12, A21. What about this? Plus B12, A22. What about this? Similarly, so it will be B21. One, B21, A12. Okay. Let's just leave it like this. Okay. What is A into B according to our matrix multiplication definition? So this is A. What will happen when you multiply these two? So it will be A11 B11 plus A12 B12, right? That's this. You can verify that all 4 will match. Okay. In fact, we could have gotten this if we had simply used the matrix notation the whole way. So we started with f of x, and then we applied the output of that with g. F of x is nothing but A of x. But g of something is simply, sorry, I did a mistake, but this is fine. Did I write it like that? Yeah, it's fine. It will be switched. So this will be wrong. Yeah. BA is essentially this. You can verify that later. Okay. That means, okay. The product of these two matrices comes out to be in this weird form. That's because matrix multiplication represents a composition operation. A composition operation is when you apply, when you repeatedly apply functions. For example, if I say I have two functions f and g, this composition operation simply means, this will give me another function, let's say h, and the way I compute that function is through this composition operation. So I take the variable that I want to apply this function on. I first compute g of x. The composition simply means you take the output of this and then you apply the second function f. Okay, that's what we've done here, right? This means when you compose linear maps, that is equivalent to matrix multiplication, right? That's what we see here. Matrix multiplication comes out, the rules for the multiplication come out in this weird form. It's because what we are doing is essentially a composition operation of linear maps. Okay. Now it should also be clear why matrix multiplication has this rule that if you have BA, the columns of B have to match the rows of A. Why? If it's a composition operation, right? You take, you have one function, an input goes in, out, and then you get an output, and then you're going to apply another function on the output. But for you to be able to apply another function on the output, the function that you choose has to be something that takes input from this space. If it's a function that does not take input from this space, you cannot do that operation. So the reason why the number of columns in B have to match the number of rows in A, it's because when you do this composition operation, you do G first and then F later. What comes out of G should be what F accepts as input. Okay. So when we had the general case here, M, P, P, N, this takes Rm, spits out something in the p-dimensional space. Okay. G takes something from the p-dimensional space and spits out something in the n-dimensional space. If this was some Q, you cannot apply G to the output of what you get from F. Okay, and that's essentially why you have the rows and columns condition on matrix multiplication. Is that clear? Okay, I hope that now clarifies why matrix multiplication has that weird form, because it's a composition operation of linear maps. Matrix multiplication. Okay. We'll now look at another very important idea. It's called the rank of a matrix. Okay. If you have a matrix A, okay, n cross n. The definition is very simple. The rank of a matrix is simply the dimension of some subspace. What is the dimension of a subspace?
It's the highest number of m for n, depending on the row of
Hey, forget about a matrix. I'm simply asking what is the dimension of a subspace? Size of what?
number of elements.
No, not the number of elements. What is the dimension of a or a vector space? Again, this is something you have to remember by now. It has something to do with the basis, right? What property of a basis? Yeah, if you have a vector space S, and if the set B is a basis for this vector space, the number of elements in that basis is the dimension of the subspace. So the dimension of a subspace S is simply the number of elements in the basis set. Yeah. Okay. So the rank of a matrix A is simply the dimension of the span of Can you say this out in words? What does it say? The rank of a matrix A is simply what? The dimension of the span of the columns of A. Okay. What is the span of a set of vectors? What is the span? It's not just a linear combination, right? It is this set of all linear combinations of a set of vectors. So when I say columns of, this is span of the columns of A, this is simply the set of all possible vectors you could have generated if you simply take the linear combinations of columns of A. Okay, and whenever you take a span of a set of vectors, you do get a subspace. Okay, so this is a subspace or a vector. This is a vector space, right? And the dimension of that vector space is what is defined as the rank of a matrix. Okay, so this essentially tells you, if I simply take the columns of A and I take all their linear combinations, I produce a set of vectors. Okay. The dimension of that subspace tells you what kind of subspace that I produce. Okay. Okay, and that's simply the rank of A. It turns out that this is also equal to the span of, this is not very obvious, but it is true. Okay. Okay. You take the rows of A and then you take all their linear combinations. The linear combination of the rows of A, you will get a vector space. Okay. The dimension of that will also be equal. Okay. This is again a very strange fact. Okay. Because what space does the span of the columns of A reside in? Is the question clear? R? Or N or Rm? Okay, where are the columns of A from? What space? Rn or Rm? Rn, no? See, A1, A2, Am. How many? A has n rows. How many elements does A1 have? N elements. That means it's from Rn. And what about this? Where is this from? Rm. So my question is, if you take a bunch of vectors from Rn and then you take their linear combination, what space is this subspace going to reside in? This is a subspace. This will be in. Okay. What would this? Where will this reside in? Rn. Okay. But it turns out, even though this resides in an n-dimensional space and this resides in an m-dimensional space, if the rank of this matrix is R, what this tells you is if you take the linear combinations away, all you can produce is a R-dimensional subspace in Rn. Okay, if you use the columns. If you use the rows and you take the linear combination, all you can produce is a R-dimensional subspace in Rm. Okay, maybe that's all too vague now, but we'll clarify that. We're out of time now. We'll clarify that in the next class. Okay, but again, this is something you simply remember for now. Okay, so we'll stop here. Are there any questions about what we've discussed today? No? Okay, all right, then we'll stop here and we'll take it again on Thursday. Okay, thank you.